Okay, so our second talk of this session is by, I hope I pronounced your name correctly, Sorawee Porncharoenwase,
Yep.
about a pretty expressive printer, which take it away.
Cool. So yeah, hi, I'm Sorawee. In this talk, I will present our new pretty printer that we call a pretty expressive pretty printer. It's formalized and proven correct in Lean 4. And so as a part of this talk, we will go over how the formalization is done and what is the design of the pretty printer. So let me start by talking about an application of pretty printer, which is code formatting. Here's a piece of code. You do not need to read it. The only takeaway from this is that it's poorly formatted and it's not readable. And so we can use a tool called code formatter to make this code more pretty, to make this code readable. Now, I don't think that code formatter is a thing yet for Lean, but it's on a roadmap. And you can read the roadmap to see why the tool is valuable, right? So it enhances collaboration, it makes the code maintainable, and so on. How do code formatters work? Well, we have the code. The next step is that we're going to pass it into a syntax tree. One thing that I would like to point out is that there are multiple styles to format for each construct. For example, the function application could be formatted in, say, the horizontal style like that, or the vertical style like that. But why? Why are there multiple styles? Well, if we only have the horizontal style, then we could have like a really long line like this. And that's not readable. In fact, the Lean style guide says that the line length should not be longer than 100 characters. And so we can make this a bit more precise by saying that there's a parameter called the page width limit. And the fact that this line has an overflow over the page width limit means that it's really bad. We don't want that. On the other hand, if we only have the vertical style, then there could be real verbose code like this. And in particular, it has a lot of wasted space. So we also don't like that as well. So it's important to have these styles and use them in a mixed way so that the code looks good. So what we're going to do is that we're going to encode these styles along with the syntax tree into an object that we call document. And then we're going to feed this document into pretty printer, which is the subject of this talk. So essentially, the pretty printer is the core of the code formatter. It chooses the styles in a way that make the output easy to read. And then the output is in the formatted code that we want. Now, as you can see, the word easy to read is pretty informal and subjective. And so what pretty printers are going to do is that they're going to formulate this task as an optimization problem to make easy to read precise. How do pretty printers work? Well, it consumes a document that I talked about earlier. This document is actually a program in a family of domain-specific languages that we call pretty printing languages. Again, do not need to read the code. I only want to say that this program, this document, encodes both the textual content and the styling choices, as I said earlier. It also consumes an optimality objective parameter. And for most pretty printers, this is going to be the page width limit. And then it outputs an optimal layout, the textual content that we want. In particular, the document encodes a set of layouts. A combination of the optimality objective built into the pretty printer along with the parameter then determines the optimal layout or an optimal layout. And the pretty printer's job is to pick this layout and then present it to user. As an example, let's say that I have a document that encodes these two layouts. They are function application in, let's say, the Python language. Well, with the page width limit of 15 and with the objective of trying to avoid overflow over the page width limit whenever possible, and then minimize the number of lines, that creates this line, the page width limit. And since both layouts are under the page width limit, the one with minimal number of lines, which is the first one, would be the optimal layout. But if we change the page width limit to, let's say, 10, in this case, the first layout now has an overflow, and so the second layout becomes the optimal one. there are many pretty printers in the literature. Why? Why isn't there just only one? Well, it's because different pretty printers make different trade-offs in the expressiveness of the pretty printing language, optimality objective of the pretty printer, and the performance of the pretty printer. In particular, we make a survey on all these different pretty printers, and we categorize them into two groups. The first one, we call them traditional pretty printers, and the second one, we call them arbitrary choice pretty printers. And their characteristics is as follows. The traditional printers has poor expressiveness, relatively, poor optimality objective, but has really good performance. On the other hand, the arbitrary choice printers has okay expressiveness, okay optimality objective, but has poor performance. And that's a bummer, because 2 years ago, I wanted to create a code formatter for the Racket language and was looking for a pretty printer to be used. And I couldn't find a good fit. So I emailed Justin, who's my co-author of this work, asking for his advice. And he said, bad news. A pretty printer for Racket is going to be either bad or slow. Now, to understand this remark, let me talk a bit about Racket. So Racket is a language-oriented programming language, which means that it's a language that facilitates language creation. And so on the right, you can see, let's say, a language for writing documentation, or you can even create language like Python inside Racket. So there are some interesting characteristics in Racket. One is that there are user-defined macros everywhere. And this is essentially a new constructs that are being added to the language, right? So there is no predefined styles for these macros. And so it's going to be challenging for code formatters to format these programs. There's also something called hash-lang mechanism, which allows you to switch the surface syntax of the program. Again, you can create arbitrary hash-lang with whatever surface syntax that you want. So again, there is no predefined styles. What this means then is that the code formatter for Racket should be extensible. And in particular, it means that the pre-printer must be expressive to support all these different styles that we may not anticipate. And so one question that might be worth thinking about is, what about Lean? Because Lean also has user-defined macros and hash-lang mechanism as well. So it's clear that these existing pretty printers are not going to suffice for our purpose. And that motivates us to create a new pretty printer that we call PyE. PyE has good expressiveness, good optimality objective, and has okay performance. So let's see how that's done. The main challenge, of course, is that it's going to be difficult to do this because there's tension between expressiveness, optimality objective, and performance. So what we're going to do is that we're going to take a look at the existing pretty printers and see what we can learn from them. And let's start with the expressiveness aspect. The traditional printers has poor expressiveness. Well, that's because it cannot express layouts that differ in more than just white space. Here's an example. These are two layouts. It is not possible to construct a document in the traditional pretty printing language to encode these two layouts. Because one of the layouts has an extra comma, this is called trailing comma. And yeah, that's just not possible. It also cannot express dynamic alignment. And by that, I mean something like this, where you indent in a way that is sensitive to the preceding content, as opposed to static alignment, where you indent by the fixed amount of space, like 2. And so dynamic alignment is not expressible in the traditional pretty printing language. The arbitrary choice pretty printing language, on the other hand, has an okay expressiveness. It can do both of this. But it cannot express what we call unaligned concatenation. And so by that, I mean, let's say I have this return statement in language like JavaScript or whatever. The way to express this, I would construct a document modularly, ideally, by saying that, well, it consists of 3 parts: the return keyword, the function application, and then the semicolon, and then I compose them. But this is not possible in the arbitrary choice pretty printing language. What you need to do instead is that you need to decompose it in the line-oriented way, which is cumbersome. No one wants to do that. And so, yeah, the expressiveness of arbitrary choice pretty printing language is not perfect either. Now, One thing that you might want to ask is, how do I know that these are actually true, right? What I just said is pretty informal. How do I know that it's true? Well, we created two formalisms that we call functional completeness and definability, which is based on an earlier work. And using this formalism, we can rigorously prove that what I claimed are all true. And using functional completeness and definability, we can also use them as a guide to create a new pretty printing language that we call Sigma E. Sigma E has good expressiveness. It is strictly more expressive than both the traditional pretty printing language and the arbitrary choice pretty printing language. And in particular, it has all the good traits from both of them. So that's it for the expressiveness. Let's now move on to the optimality objective. Well, traditional pretty printers has poor optimality objective, but if you take a look at the literature, you would find that it says the opposite. It says that traditional pretty printers has good optimality objective. It produce text with minimal number of lines while not exceeding the page width limit whenever possible. That's really great. It turns out that that's not actually true. And here's a counterexample. It is possible to construct a document in a traditional pretty printing language to encode these two layouts. And according to the claimed optimality objective, the left one should be the optimal one. But what the pretty printer is actually going to output is the right one. That's the optimal layout according to the pretty printer. And that's neither minimizes the number of lines nor avoiding overflow whenever possible. And the reason that it does that is that it uses 3D algorithm, which cannot plan ahead into the future to pick the optimal one. The arbitrary choice printers, on the other hand, has an okay optimality objective. It does minimize the number of lines whenever possible, and then avoid overflow whenever possible. But it cannot cope with unavoidable overflow, which means that if you have, let's say, a really long string literal, it's gonna overflow however you format it. And it just gives up. It's just like error. So that's kind of like bad from the usability perspective. Now, what can we learn from this? One, we do not want to use greedy algorithm because it's not optimal. Second, we want to be able to cope with unavoidable overflow. But in particular, a better idea is that we will allow users to specify optimality objective, right? Let's say that there's a concept of overflow that we want to minimize. Then that will automatically make it possible to avoid unavoidable overflow because, well, there are multiple ones. We just pick the one with the minimal overflow. Things work. And so using these insights, we create the pretty printer PyE to use dynamic programming in order to avoid the greedy algorithm. And we also have a concept of cost factory, which allows users to specify optimality objective. I'm not going to go into the detail about what cost factory is. Just simply that is some kind of algebraic structure that allows you to specify the cost type, operations on the cost type, as long however you want, as long as they satisfy some kind of axioms. All right, the last bit is good is performance. The traditional printers has good performance, but that's simply because it uses greedy algorithm, which we are not going to do. The arbitrary choice pretty printers, on the other hand, has poor performance, and that's because document in the arbitrary choice pretty printing language is actually a directed acyclic graph or DAG, like that. But many pretty printers in this family treat the document as a tree, and so it unfolds a structure which makes its size could be to be potentially exponentially large compared to the size of the tree, and that makes it inefficient. And so one of the lessons is that we really need to be careful to not unfold the DAG structure. And in our pretty printer, we use memorization on the document identity to do just that. And since we don't have the greedy algorithm, we also need to optimize heavily. And that's done by using a concept called computation width limit to aggressively prune suboptimal layouts, along with a data structure like two-dimensional Pareto frontier to efficiently track optimal layouts. And so these are the key ideas of our pretty printers to make it have good expressiveness, good automotive objective, while still being reasonably efficient. To summarize, PyE consumes, which is our predictor, consumes a document in the sigma E predicting language. It has the parameter, which is the cost factory, and it also consumes computation with limit for aggressive pruning. And then it outputs the optimal layout. At the core of PyE is a function called resolve. It consumes a document which encodes a set of layouts shown on the bottom left, consumes a configuration, and then outputs a set of layouts. This set of layout in particular forms a Pareto frontier, which is a trade-off between two quantities, cost and last. Cost is essentially the cost of the layout, which is computed from the cost factory that I talked about earlier. And last is the length of the last line of each layout. Now, in case you, let me remind what Pareto frontier is. Pareto frontier is a set of things that are not dominated by other things, right? And so, for example, in this diagram, we have the blue layout dominating the orange layout because it's better in both axes. It's better in both cost axis and in the last axis. And so what resolve is going to do is that it's going to output this Pareto frontier, right? This is a set of things that are not dominated by other things. Now, also, this is actually not a full Pareto frontier. We are going to discard layouts that exceed the computation width limit aggressively. And this is where the computation width limit comes into play. What does it mean for PyE to be correct? Well, let's talk about the correctness of resolve, which is our main function here. There are two things. The first thing is optimality. It means that every layout encoded by the document is dominated by a layout in the output set. Okay, and so this is an optimal output set because it dominates everything. This, on the other hand, is not an optimal output set because there's a layout like this blue layout that is not dominating, dominated by the output set. The second part is validity. It says that layout in the output set is indeed encoded by the document. So this again is a valid output set because every single one of them is encoded by the document. On the other hand, if we have this thing, right, as the output set, well, it's very optimal. It has really low cost, but it's not encoded by the document. So that's not good. That's not valid. So let me now give you our project tour. So this is kind of like the structure of our proof, of formalization and proof. The goal is to get into these three files at the bottom. This one says that this one is the validity theorem. This one is the optimality theorem. And this one is about the efficiency, but we're not going to get into that in our talk today. All right. So yeah, we start by defining what does it mean to be a layout. A layout can has either one line, a single line, or multiple lines, right? And then next we define the cost factory, which is parameterized by the cost type. And then you can implement the operation however you want, but you also need to provide a proof that it satisfies these axioms. And then we can start defining the document structure. And then these two relations provide the semantics of the document. Essentially, they define what it means for a document to encode a set of layouts. And then there's some mechanism, some machinery, yada yada. And then we have the concept of Pareto frontier here. This is what it means to be a Pareto frontier. We have kind of like, Pareto frontier merging and stuff like that. And then we can define the resolve. We can formalize the resolve function using this relation. And then now we can prove about this resolve relation, right? This one here says that resolve is valid. This is the validity theorem. It says that, well, every layout that is produced by resolve is going to be valid. And the last one is the optimality, which says that if it outputs something, right? If it outputs this output set, then that's gonna dominate everything. Yeah. There's some caveat about the combination with limit there, but yeah, that's pretty much the gist. So let me now go back here and give you some of my thoughts on Lean. So Lean 4 is very great. I used to have a formalization project, another formalization project in Lean 3, and switching to Lean 4 is really enjoyable. To give you one example, I used to have like a large set of macros to manipulate the proof context in Lean 3. And when I switch to Lean 4, I do not need any of that because things work just fine. Yeah. GitHub Copilot works really great with Lean. I know that there's kind of like a specialized tool now for Lean to do this AI thing, but in the last year I don't have that, and so I just use GitHub Copilot, and it works really great. It can autocomplete like proofs, and it can even kind of like suggest dilemma that I do not know that they exist. But do not let it autocomplete theorem statement because I mean this is the specification that you want, right? And so yeah, I made this mistake once, and it took a really long time to debug it. Lean has a really great community. I asked questions on Sulip and got really great help. So thank you for all of that. One thing that I find kind of like annoying is the recompilation during editing. So let's say if I have a large file and I edit in the middle, that's gonna recompile the whole file, and it takes a really long time. It makes CPU hot. It makes my laptop hot, and yeah, I mean generally I prefer kind of like the experience that I got from Proof General, where you kind of like can mark which part to get submitted to the engine. But yeah, that's pretty much it for the formalization. Implementation wise, well, we implement PyE concretely as a pretty printer that we call pretty expressive. One of them is in Racket and the other is in OCaml. And the Racket one is also used, as the foundation for the code formatter for Racket that we created as well. So there are a couple of other things in the paper. There's a survey of existing pretty printers in the literature. There's the details of our full pretty printing language. There's the details of our pretty printing algorithm, our time complexity analysis, and the formal framework to compare expressiveness. So stuff like functional completeness and definability. And then we also have the evaluation of pretty expressive against other pretty printers. See how it works in practice. But yeah, that's pretty much it. This is a pretty expressive printer. It has good expressiveness, good optimality objective, while still being reasonably efficient. So yeah, thank you, and I'd be happy to take any questions.
Thank you. I see that there are already some questions. The Huskinson Center has a question.
So that would be me. So I have the obvious question that everybody has. So when do we get a code formatter for Lean 4 using this thing?
So one sec. I want to kind of like switch back to the Zoom layout, but I do not know how. Am I sharing my screen right now?
Yes.
Okay. I need to find a way to disable. Okay. Cool. All right. Hi again. Can you repeat the questions again?
So when will we get a code formatter for Lean 4 using this?
Actually, I do not know. I'm not a part of that. I think David might be able to answer that. So yeah.
But what is required to do that? I mean, how would that work if someone wants to use your technology to build a code formatter for Lint4?
Yeah, that's a good. David, do you want to chime in? Because like I think this is kind of like a question for you.
I think this is actually not really a question for me in particular. I'm not working on that aspect of things. It's, you know, it's a thing that we have in our roadmap that we're going to do, but I don't have a particular date on it at the moment off the top of my head.
So maybe I can answer the question. I am supposed to work on the formatter for the FRO, and I did read the paper. I actually have a not so efficient implementation of your algorithm in Lean already, and I do plan on making the formatter with that, yes. But I don't have any expected time of arrival either, of course.
I saw that, David, you had a question yourself?
I mean, the question was whether your formalization is usable as a pretty printing library as well, or whether it's sort of done differently to make the formalization easier in a way that wouldn't actually make it practical as a pretty printing tool.
Right. So there are a couple of things in the actual implementation. I have more constructs, like have more features, and so those features are not formalized. So that's one thing. But another thing is that I make everything relation in the formalization just to make things easy for me. So yeah, it's not going to be runnable. So
That makes sense.
another,
Cool.
yeah.
And if I may ask a little follow-up, how feasible would it be to extend this technique to layouts that have different notions of like concatenation, or like I'm thinking, for example, a table layout. If you know, like let's say you have you know, some pattern matches and you want like a multiple pattern match, you want them to all line up in columns with each other or something. Is that
right?
Like I don't think it's expressible in the library as given in the paper, but is that like possible to extend, or would that just be like a throw it all out and start over thing?
So it is possible somewhat. I actually experiment with this a bit because, like, you know, it's actually a pretty popularly requested feature. So you can do that by using a choice. So essentially you expand into multiple choices, and for each choice you essentially for each possible alignment you kind of like you say that, well, please try to do it, but if it fails, it fails, and then you try to adjust the cost to try to minimize to try to get the leftmost one. So yeah, it's possible. It's going to be very expensive. But yeah, and also it's limited to essentially 2 columns, so that's also not great. But yeah, it's worth thinking about.
Thanks.
Alexander, did you have a question, or is it already answered?
Yes. Just to clarify your answer, the answer that you just gave to David. So you think that the formalization link is usable as a library to implement a preprinted for, let's say, a language that I implement a parser, or the other way around? So it is
not. Like, I mean, you cannot run this as a pretty printer in Lean. Yeah.
Okay. Thank you.